Hey y'all, it's Mr. Boyd and I'm back at it again, and today we're going to start talking about vectors. As you can see, we've got the dogs on the screen today. We got Haley on the left and Moses on the right, and they're on here because they're going to be one of the things that I actually use to talk about and try to help you understand vectors, because there's a lot of places in my life where I think about vectors or where I use an understanding of vectors to kind of understand what I need to do, and the dogs are just one of those places, walking with this leash, that comes up. So we'll talk about that a little more in a second. Let's talk about some examples of vectors first before we get in. Let's start here. Take a look at these trains. And my question for you is, what do the arrows tell you about the train or about the trains? Well, we can probably see pretty easily that this one on the bottom is a little bit, or the one on the bottom is a little bit shorter, and the one on top is a little bit bigger. So what does that tell you? So when I do this in class, people say things like, it means the top train is going faster, or the top train is stronger, or the top train is pulling a heavier load. And really, any and all of those are right because we don't really know. It doesn't really say anything about the trains, although your intuition is right that there's something going to the left because of the arrow, and the thing on top is the one that's longer or the one that's bigger. Before we move on, let's get a little bit of vocab around vectors. Okay, first we have the initial point. That's going to be sort of like the point of origination or the point that does not have the arrow. So there's the initial point there. You're going to hear me call this the tail of the vector. That's sort of a colloquial way of saying the same thing. The terminal point, that's where it ends. It's over here where the arrow is, the direction that it's pointing. You're going to hear me call this the head. It's like a head and tail. And then the magnitude. The magnitude can most easily be understood, at least for now, as the length. Now, when we talk about specific vectors, the magnitude could represent how hard the train is pulling or how fast the train is moving, something like that. Let's look at another example. And guys, I'll just be honest with you. I don't exactly know what this is showing in this picture, but I do know that it's a big old vector field, okay? And so maybe one of the ways that would be easy to think about this is if this were the wind and weather patterns across the United States, or the eastern half of the United States, okay? And so you can notice, like down in here, we've got shorter vectors here. You've got a vector with a similar direction that's a little bit longer. So for example, if this is wind, we would call this wind speed. And the longer the vector, the faster the wind's going. So right down here, like in Kentucky, the wind's not really blowing right now. There's really not a lot of wind at all. I mean, maybe just like 1 mile an hour or something. Versus like you get over here into like Oklahoma, Texas, Kansas, Nebraska, you've got a really strong north-northwest wind. Okay, so that's one way that we can use vectors to represent some sort of real-world concept. You've probably seen this on the news or something like that. Okay, specifically, in terms of like definitions, a vector is a way of expressing a magnitude and a direction. So with the example we just saw with wind, the magnitude was like how fast is the wind? And the direction, well, I think you know what direction is. I mean, you could describe it as north or south or east or west, but all the directions in between as well. For me, I think it works best if you think of vectors as directions. And I don't mean direction, I literally mean directions. Like, hey, if you wanted to get to my house, go 4 blocks west and 5 blocks north. Or like, go 4 blocks, hang a right, and go 5 blocks, something like that. Okay, if you think of it as directions from how to get to point A to point B, that I think will serve you pretty well in these next couple of lessons. And then here we've got another example. So a minute ago we talked about speed, like wind speed or speed of a train. Here we have force vectors. This is a picture that I took while I was walking my dogs, and you can see this is the leash right in here that I'm holding, and I have a splitter here. Well, one of my dogs is pulling to the right, and one of my dogs is pulling forward. So those are two different vectors. If they're pulling those directions, the actual pull that I'm experiencing is going out in that direction somewhere. And since this is a street over here, I probably want to make sure that I pull in the opposite direction to make sure they don't go into the street. We'll actually see a specific story problem this in the next lesson, but let's get through the very basics in this video today first. Okay. In terms of notation, there are 3 different ways that we're going to use to write vectors. Over here on the left, the 3 that I have are all equivalent. They say the exact same thing. And here's the good news. They work the same way that coordinates do. So for example, if it said 2, 4, and we had it like coordinates, -4, and we had it like coordinates, you would probably know to go 2 to the right and down 4 and put a point, and you would know that was the point. Well, if it's a vector, all it means is we're going 2 to the right and down 4, but it is a vector that does that. Now there is one key difference. I drew this from the origin, but there's nothing that says up here that it has to be the origin. And if you think back about the definition of a vector, that it's a magnitude and a direction, it's not a location. So there's no reason that I couldn't have started right here and then gone 2 to the right, down 1, 2, 3, 4. That is the same vector. And you go, wait, but it's in a different spot. Yeah, but that's okay. It can still be the same vector in a different spot. It's the same vector. It's some object. Okay, all three of these forms are exactly the same. This one says 2i minus 4j, and this one says 2 comma negative 4. It's in column. You can see that it's written as a column, I hope, and that's why it's called column form. This one's a linear combination, and this one is component form. It's just listing out the components. Now, one thing to be aware of, and this will come up very shortly, we can also write vectors in 3 dimensions. So the third dimension, first dimension is left and right, second dimension is up and down, which means the third dimension, if I could show it, and I can't because I don't know how to do that on a 2-dimensional screen, but it would come right out of the screen coming right at you. Now, if we wanted to write these in 3 dimensions, the first one, we would write 2, negative 4, and then whatever the third component was, we just write it. Maybe it's 5. It's coming out of the screen 5 units. The second one, we would do 2i minus 4j plus 5, what do you think the next letter is? H-I-J-K-K. Yeah, alphabetical order. Okay, that's all it is. And then column form, you just add another component in the column. So 2, negative 4, 5. And here's the deal, guys. 3 dimensions is not harder than 2. And 2 dimensions is not harder than 1. All it is there's just 3 things going on. You don't have to combine all of them together even. One of the things that's going to be really nice about vectors is vectors give us a way of taking something in multiple dimensions and thinking about them in 1 or 2 dimensions at a time so they become a little bit easier. Let's talk just a little bit more about that IJK deal. Okay, so these are what are called standard unit vectors. Now, just as the unit circle had a radius of 1, unit vectors have a magnitude of 1. So let's look at I. I is saying it goes to the right. It doesn't go up and down. It goes to the right by 1. There's a picture of it there. J, it's saying it doesn't go right or left at all, but it does go up 1. We have a visual of it there. So if that's I and that's J, what's K? Well, this one's only to the right. This one's only up. K is the third dimension, so that means that would come 1 unit out of the screen. Like from right here, it would come out of your screen, popping out at you right now. Okay, and we would describe that as 0, 0, 1. Since K is in the third dimension, we need that 3-dimensional column vector in order. Now that we have a few notes on notation, let's get into a couple of basic examples. Okay, let's do one where someone walks home from school. After school, Tommy walks 1 block north and 3 blocks west to China Lake Park. Then he walks 2 blocks west and 4 blocks south to get home. We want to write his trip as a single vector. We're going to do this both arithmetically on the left and visually on the right. So let's start with arithmetically. Let's write out that first vector for when he walks to the park. 1 block north and 3 blocks west. Now be careful, because that first number, remember, that's left and right. And we think of north as being up and south as being down, west and east. So 1 block north is actually 1 block up, so put it down here in the second component. 3 blocks west, a lot of people write 3, but west is to the left, and so we want to represent that mathematically. Let's do the second vector. Then he walks 2 blocks west, so I think that's -2, and 4 blocks south, so -4. We want to write that trip home as a single vector. Well, let's try sketching it and see if it makes sense. I'm going to pick some starting point because, guys, it says they start from school, but I don't know where the school is on here. This is just an arbitrary graph. So I just pick a spot, any spot, and it says go left 3 and up 1. So left 3 and up 1. There's the first spot. So if that's school, that's the park. And I'll draw in the vector. And then 2 blocks west, 4 blocks south. So 2 blocks west, 1, 2, 3, 4 south. And that must be home. We're asked to write that trip as a single vector because right now I've written it as 2 vectors. So what we can do is we can basically ask the question, like I said, think about a vector as directions. If we had to give directions from school to home, what would be the easiest way to do that? To get from school to home. Well, we might say go south 1, 2, 3, like this, south 3. And then once you're south 3, we go west 1, 2, 3, 4, 5. So -5. So there's a little bit of a shortcut I can show you here, guys. How could we have taken these first 2 vectors and turned them into that final vector? The quickest, easiest way is to just add them together. Like -3 plus -2 is -5, and 1 plus -4 is -3. So this is an example of vector addition. And we can see that in the picture. The thing I want you to notice, look at how these first 2 vectors are oriented. They go head to tail, and what I mean by that is the head of one of the vectors meets up at the same spot as the tail of another. Anytime you have a head to tail orientation, that's going to be vector addition. And I guess technically it could be subtraction, but addition and subtraction are essentially the same thing, so that still works. Okay. Let's do a little bit more specific work on what vector addition looks like and how to do it. So let's try this example. Okay. If at any point during this example you feel like you've got it down, please feel free to pause the video and proceed on your own and then use the video to check yourself. Okay, guys, let's do u plus v first. All I'm going to do for that is I'm going to write u and v. So there's u and there's v. And then we're just going to add straight across left to right. And like I said earlier, one of the nice things about vectors, it allows us to take something in multiple dimensions and look at it one dimension at a time. So let's look just in this x dimension, the left and right first. So that'd be 2 plus negative 3 is negative 1. 5 plus 1 is 6. I also want to show you what that would look like visually. So let's start right, I'm just picking a spot, okay guys, it's totally arbitrary. So that says to go 2 to the right and up 5, so 1, 2 to the right, up 1, 2, 3, 4, 5. Since it's vector addition, I'm going to orient them head to tail. By the way, if it weren't head to tail, it would look maybe like this. That would be tail to tail, where the two tails meet up in the same spot. That's different than what I'm about to do. What I'm about to do is what this says, left 3 and up 1, starting here where I left off, so left 1, 2, 3, up 1. So that's what it looks like. That's u and that's v. And let's double check what that resulting vector is. So how do I get from there to there? Is it true that we go left 1 and up 6? Yeah, left 1, up 6. Sure it is. So that's the vector u plus v. Okay, and that's what it looks like. When you do vector multiplication, that's even easier. All that is you take the 2 like it says there, you write the vector v, and you distribute it in. So you just double all the numbers. So negative 6, 2. Done. Those are easy. Okay, what about the next one? This just combines the first two. So we write u, 2, 5, minus 3 times negative 3, 1. We'll do the multiplication first, like aka PEMDAS, right? So 2, 5, minus 9 and 3. Although, wait a minute. I have to be a little bit careful here. Because am I doing negative 3 times negative 3 and getting 9? If I am, that would be a plus because the negatives would have canceled out. So you know what? I think that's actually what I'll do. I think I'll say I distributed the negative as well, so that becomes a plus. But if I distributed the negative, that becomes a negative 3. I think I can write my answer now. So I get 2 plus 9, that's 11. And I get 5 plus negative 3, that's 2. All right, if you're feeling decent at all, try the last one on your own now. Okay, and I'm going to go ahead and show the work as well. But I'm going to be kind of sneaky. I'm going to actually do the work in my head. So I'm going to write down 2u at first, meaning all I'm going to do is I'm going to look at u. I'm going to double the numbers. So double 2 and that becomes 4, double 5 and that becomes 10. Then I'm going to put the plus like it says. Then I'm just going to multiply the v values by 4. So v is negative 3 multiplied by 4 is negative 12. And 1 multiplied by 4 gives me 4. Add them together and I get negative 8 and 14. Okay, and that's all vector addition, subtraction, and multiplication by a scalar are. By the way, I'm using the word scalar. When you're multiplying by a whole number, that whole number is called a scalar. And that'll come up a few times in the unit as we go here. Another example. In this one, we have a little bit different notation. I hope it'll be intuitive to you that looking right here, this is a vector that starts at point A. See, A is over here by the initial point. And B is over here by the terminal end of that thing. It starts at A and goes to B. This is a vector that goes from B to K, and then we have a couple questions here. So what I think might be helpful is if we try to sketch this. So again, I'm just going to pick a spot on the graph. It does not matter where I start. I'm going to try to sketch AB, which means I've just written down point A. So now I'm going to try to find point B. 3 to the right, down 2. 1, 2, 3, down 2. That must be point B. And then this tells me how to get from B to K, like directions. Remember in the beginning I said think about it as directions. So how do I get from B to K? I go 5 to the right, and I go down 4. 1, 2, 3, 4, 5, down 1, 2, 3, 4. And so what I hope this will impress upon you, there's point K, what I hope this will impress upon you, see right here, this is head to tail? Even though it doesn't say so, that indicates to us that this is a vector addition question. So if I want to find AK, because this goes A to B, B to K, I'll just add those two sets of directions together. So 3 plus 5 gives me 8, and then negative 2 minus 4 gives me negative 6. And we can confirm that. This says 8 to the right and down 6. Is it true that from A to K is 8 to the right and down 6? Let's see. 8 to the right, down 6. Yeah, visually that appears to be true. What about the second question? From K to A? Well, that's the exact opposite as A to K. So if A to K, I had to go 8 to the right. To get from K back to A, I would have to go 8 to the left. So all I write then is negative 8i, 8 left to undo that. And if A to K was going down 6, then K to A is going to be going up 6. So that'll just be plus 6j. Now, when we do addition, it is possible that vectors could totally cancel each other out. In fact, that's what's happening in these pictures with the dogs. Right here in the middle of the picture, we have Haley pulling to the right, and we have Moses pulling to the left, and they have no impact on me at all. In fact, I don't know if you can tell or not, but the leash that I'm holding here actually has slack in it. I'm not pulling at all. They're pulling on each other, but not on me. And that's why I like this thing that I bought, is because it makes it so instead of the dogs pulling on my arm, they end up pulling on each other a lot, and they can cancel out their forces. Okay, and so a lot of people will walk down the street walking two dogs. If your dogs don't pull, that's totally fine. My dogs like to pull, and actually I kind of like them to pull so they wear themselves out. And because of that, this is a way that they can sort of wear each other out instead of wearing me out. I'm wondering, can you think of any other examples of opposite and canceling vectors? I'd actually like you to pause the video and brainstorm for just a minute. Can you think of a case where two vectors cancel each other out because they're exactly opposite? Here's a couple of examples that I like. I had a student in class this week say that a treadmill is an example. On a treadmill, you're trying to run forward, but the treadmill is pushing you backward, and so you're not going forward or backward. Your speed is being canceled out by the speed of the belt on the treadmill. Another example, if you've ever tried to swim up a river, if you try to swim up a river and the river is pushing you back, you're probably going to be staying in the same spot. So are you swimming at some speed? Yeah, you're swimming at some speed upriver, but the river is canceling that out by pushing you back. Another example, and this one is kind of bigger and I really like it, is tug of war. In a game of tug of war, you could have like 10 people pulling this way, and you could have 10 people pulling this way. And even though all the people are different sizes, and even though they're all pulling with different forces, they can still cancel one another out. Kind of cool. We now need to talk about the magnitude of a vector and how to find it. The easiest way to think about this is if you consider the magnitude to be the length of the vector. The notation is right here. This is one of the things that in my experience students often forget. When they see this notation, they fail to connect this to the magnitude. So please sort of star this or do something in your notes so you recognize that both of these mean the exact same thing. They are not saying absolute value, they're asking for the magnitude. So here's how we find it. Find the magnitude of 3, negative 5. All that says is a vector that goes 3 to the right and down 5. So 3 to the right, down 5, we're asking what that length is. Well, guys, look, that's a right triangle. And so if you have a right triangle and you know two side lengths and you don't know the third, that's the Pythagorean theorem. So 3 squared plus 5 squared, and then we're going to take a square root of that. So what is that? That's 9 plus 25 with a square root, so that's square root of 34. So when I teach this, what I say is rather than saying Pythagorean theorem, and yes, there's a formula in the formula book, what I say is square 'em, add 'em, root 'em. And here's why I like that. Because if it's in 2 dimensions, it's really easy to understand that it's the Pythagorean theorem. However, what if this vector had a third dimension? Like there was a 2 down here. Well, that shakes things up. For most of us, it's really hard to think about the Pythagorean theorem in 2 dimensions or in 3 dimensions. But this process up here totally applies. And when I say I mean the components. So what I'm going to do then, I'm going to grab each of these components, 3, 5, and 2, and I'm going to square them. Now, one thing that might be confusing right now is why am I not taking the negative? It seems like I'm being really lazy, right? I am being a little bit lazy, but what I'm noticing is that I'm about to square that number, and anytime you square a number, it becomes positive. So bringing this negative over doesn't actually do anything, meaning all it could possibly do is confuse me. So I'm going to leave it behind based on that understanding. So back to the process. Square them, add them, I'm just going to stick pluses in between each of them, root them. Okay, we already saw that that right there is 34. 2 squared is 4, so we get root 38. The reason I like this up here, square them, add them, root them, is because no matter how many components the vector has, you can always do these 3 things in that order and you will always get the magnitude. Now, if you're ready, pause the video and try the second one. Here I go. Square them, add them, root them. The components are 2 and 1. I square them, I add them, I root them, and I get root 5. Done. That's a magnitude. That's how long the vector is. Okay. This is something, if you ever get a question like this on a test, you should be really excited because it is easy. Easy. All right. What about a unit vector? Now we get to do just a little bit more thinking. Okay, a unit vector is a vector which has magnitude 1, so I'm going to write it like this. The magnitude is 1, and we have to write it in the same direction as this. I think I'm going to sketch this vector so we can try to understand it. So that's a vector that goes right 3 and down 4. And we need to write a unit vector in that same direction. So I want to make up a little side example to show you the concept over here, and then I think you'll be able to get it. Let's say I had a vector like 7, 0. 7 to the right, and then up and down. What's the length of that? It's 7. So if I wanted to write a vector that was a unit vector in that same direction, right only, I would just make it 1 and 0. That still goes only to the right, and now its length is 1. So the question is, how do I get from here to there? And please don't say subtract 6, because where would you get 6 from? The easy way to do it is to divide by the given magnitude. And when I do that, 7 divided by 7 gives me 1, and 0 divided by 7 gives me 0. That's going to be the process for how we get a unit vector. So in order to find a unit vector, what we're going to do is just divide by the magnitude. Which means we'll need to find the magnitude. Square them, add them, root them. So 3 and 4. Square them, add them, root them. Some of you already know that's a 3, 4, 5 triangle. That's awesome if you do. If not, you're doing this and you're getting root 25, and you need to recognize the square root of 25 is 5. So then all we do is we take the components of the vector, 3 and negative 4, and each of them gets divided by 5. This now is a unit vector, and that answers the question. And that would be useful if we wanted to write a vector for a specific magnitude. Now in our next lesson, we are going to get into some really specific applications and some real-life ways that vectors are used. Today we're just practicing basic skills. That'll actually be useful in that in a minute. But let's just focus on the math type questions for now. Okay, so write a vector in the direction of 4, negative 5. It helps me if I sketch it. So 4, negative 5 that has a magnitude of 5. So again, let's do a side example to make it easier to understand. A minute ago, we had the example 7, 0, and we scaled that down by dividing by the magnitude of 7. We had 1, 0. Now, if I wanted to take that and write a vector with a magnitude of 5, well, it only goes right, so I would just make it go 5 to the right and none up and down. So here, we divided by 7 to get from the first vector to a unit vector. I'm going to make a note, that's a unit vector. How would I get from the unit vector down to my desired magnitude vector, in this case 5? Well, you could just multiply the whole thing by 5. 5 times 1 is 5. 5 times 0 is 0. That works. So that's what we're going to do here. Okay, that's the process I'm going to walk through. So first we'll find the magnitude. Square them, add them, root them. 4 and 5. Square them, add them, root them. Okay, when I add those together and square them, looks like 16 plus 25. I get root 41, which doesn't look like I can simplify it. So let's write out a unit vector. A unit vector is going to look like 4 over square root of 41i. Oops, except I just crossed out the numbers. Let's do a redo on that. So 4 over root 41i minus 5 over root 41j. That's a unit vector. And then if I want to get a vector that has a magnitude of 5, I'm just going to take this whole thing. Well, I'll do it as parentheses though. I'll take this whole thing and multiply by 5. Like this. And since that's a minus, we absolutely get to distribute that. So what do I get? I get 20 over root 41i minus 25 over root 41j. And that now has a magnitude of 5. Now I'm not going to leave it like that because that has irrational numbers in the denominator, so we're going to rationalize it like this. So we'll get 20 root 41 over 41i minus 25 root 41 over 41j. And that now is a vector in the same direction as 4i minus 5j that has a magnitude of 5. Hope you enjoyed this first video. We'll get into applications in the next one, and we'll see you then.